case. When you're using an exponential function to model things with a certain growth rate, there are two formulas to use. So one is called the compound interest formula. So I mean, it's compound interest, sort of like in terms of money, but you can actually use it for other purposes also. So basically, it's when you have some kind of growth rate that compounds at specific times in a year. So you can use the compound interest formula. All right, so this is the formula here. It has a few different parameters, right? So A, P, R, N, and T. And what those parameters stand for is the following. So P is called the principal, which means the initial amount. R is the annual percentage rate, sometimes abbreviated APR. So one thing to remember about the annual percentage rate is you always write R in decimal form, right? So for example, if you have 4% in decimal form, so what is that? 4% is you divide by 100, right? So 4% is the same as 0.04 in decimal form. So that's what I mean by decimal form. So R should always, it's typically given as a percentage, but when you use the formula, you need to use it in decimal form. And the other thing is that you have to pay attention to whether it's an increasing rate or decreasing rate. So it's R is positive, it's increasing, and it's negative, if it's decreasing. And then the other parameters, N stands for the number of times in a year that you compound. T is the total time that this is in effect for, so in terms of years. And finally, A is the total amount that you want to calculate after you've compounded all the interest. Okay, so that's the compound interest formula. And the other formula is called the continuous growth formula, where you're in a situation where you're not compounding at specific times, but it's always compounding. So that's basically this formula here. And it basically comes from what happens when you take the other formula and you let the number of times goes to infinity. What happens is that thing approaches what's called the natural number, or sometimes it's called Euler's number. And even though we use the letter E, it's not actually a variable. It's a specific number, kind of like how pi is a specific number. Right? So pi is 3.14. Well, E is 2.718. About, it's an irrational number, so it has an infinite expansion. So basically, as long as you have any scientific calculator that's more than a basic calculator, it should have a button for the number E, kind of like how it has a button for pi. So on this calculator here, right? So there's two ways to get E, right? So if you just want the number E, that's above the division symbol, right? So if I press second, and then this button here, see, so you get lowercase e, and you see the number is about 2.718281828. The other way to get E is as the exponential function, right? So you see how above this button ln here, there's e to the x. So if you press second, so this is when you need to raise e to some power, right? So like say if I want to do e to the first power, which is just e, you get the same thing, right? So if you just want e by itself, it's this thing here. If you want the exponential function e, then that's above the ln button here. Okay, so So that's E, and then P, R, and T is the same before, right? So the initial amount, growth rate, and the time. Okay, so so in this example, right? So here it says it has an annual growth rate of 7%, and the initial population, right? So that, what does that mean? That means R is 7%, but as a decimal, R has to be 0.07, right? And then it says the population is initially 15,000, right? So that has to be P, and the years is 2000. So okay, so it says give the function in the form a times b to the t. Well, what we want to do is to use the compound interest formula first and then put it into this form, right? So it doesn't specify the compounding, but it doesn't say that it's continuous, right? So we can just assume that it compounds 1 times per year. So let's say n is equal to 1, right? So if you use the formula p equals, wait, it was a equals p times 1 plus r over n to the nt. Right, so now let's plug everything in. A is equal to, was p was 15,000, 1 plus 0.07, n is 1, 1 times t. And then if you simplify this, you get 15,000 times 1.07, right? Because this thing divided by 1 is just 0.07, and you add it to 1 to get this, and then 1 times t is just t. Right, so this is A, and this is B. Right, so now it's exactly in this form. Okay, so the second part asks to calculate the population in 2005. Well, we assume that t equals 0 is the year 2000. So that means that 2005 is 5 years later, so that means t has to be equal to 5. So we just use the function that we have in the previous part, right? So that's 15,000 times 1.07, and then t equals 5. Okay, so now we have the model for the function, and so we just use the function to do the prediction. Right, so we see that after 5 years, how much does the population grow to? So we just do this calculation. So one thing to keep in mind now is that when we're dealing with the exponential function, basically almost all the calculations are done using a calculator. And so you want to be familiar with how to use the calculator to calculate things. So in this particular case, you can just calculate exactly as it's written. Right, so 15,000 and times, I'll use the parentheses, 1.07 raised to the 5th power. Right, so I can just enter that all into one line, and it'll do the calculation. So it'll grow to about 21,000. 38, I guess it's rounded down. 21,038. Okay, so that problem should be similar to this one. There's also question 6, which is kind of similar, but it says continuous growth rate, so you have to use the other formula instead of the compound interest formula, but it's kind of the same idea.